All right, so luminosity is how much light comes from a star in a given amount of time. This is also known as absolute brightness. And there's something else called apparent brightness. Apparent brightness is the amount of light hitting a certain area in a certain amount of time. So rather than how much the actual star is giving off, it's how much are you getting. Okay, so there's absolute, how much is the star actually giving off? Apparent, how much are you actually getting? Now, two stars with the same absolute brightness, the one that's closer is going to have a larger apparent brightness. And so in order to change this, we have to correct for the distance. So if you can imagine you're driving and you see two stoplights ahead of you, right? The one that's closer looks brighter to you, even though it's probably the same manufactured stoplight in both cases, right? So the apparent brightness, the one closer to you looks bigger or more, has a larger apparent brightness, but the one further to you and the one both have the same absolute brightness. So how does this work? As the light leaves the star, the light gets diluted, it spreads out, right? And so depending on how close or how far away you are, it's going to spread out actually proportional to the distance. So the apparent brightness is inversely proportional to the distance, which basically means it's an opposite relationship, right? So the apparent brightness will go down as your distance goes up, or as your distance goes down, the apparent brightness will go up, okay? Now the square just means that, you know, 2 squared is 4, 3 squared is 9, so it's not a one-to-one relationship, it's a squared relationship. Here it is in a mathematical format, sort of. Apparent brightness, right, so that's kind of what we see, is proportional, that's that little alpha, to the luminosity, or the absolute brightness, divided by its distance squared. So how much is actually giving off and how far away it is, those two things will give you your apparent brightness. Alright, so if two stars have the same luminosity, that means the same absolute brightness, and they're equal distance away, they will appear to have the same apparent brightness. Right? They will appear to have the same brightness. So if they're equal distance away and they're equal luminosity, or absolute brightness, they're going to look the same to you. However, if two stars have the same apparent brightness, then one of them could be further away or have a larger luminosity. Right? So if they both look the same to you, they could be the same, or one could be further away with a brighter luminosity, or a brighter absolute brightness. So if the star has a larger apparent brightness, so it looks brighter to you standing on Earth here, then one of two things, or maybe both, are happening. It has a larger luminosity, so that means a larger absolute brightness, and or it's closer to you. Now, stars that appear kind of dull to you in the sky, not very bright, faint, two things could be happening. They could have a smaller luminosity, and or they could away. So there's a couple different things we need to know if we're going to figure out luminosity, or actual brightness, absolute brightness. Right? So we need to know its apparent brightness, and we need to know its distance. Just like if you look at the equation, if luminosity is what you're trying to figure out, then you need the other two variables, right? If apparent brightness is what you're trying to figure out, you need luminosity and distance, the other two variables. If distance is what you're trying to figure out, you need luminosity or apparent and apparent brightness. So whatever one you're trying to figure out, you need to know the other two. All right, so here's a scale of apparent brightness, okay? Apparent luminosity. And what's interesting about this is the brighter we see it, so the larger the apparent brightness, the smaller the number. So the sun is a negative, very small number, negative 26.7. The moon is a negative 12.5. right? 0 is Alpha Centauri. And then you get into other things. Now another thing to note about this scale is that it's not linear. Okay, it's actually exponential, which means that it gets brighter faster, or duller faster, I should say. And again, the smaller the number, the higher the apparent brightness. Right, so the brighter it looks. The smaller the number, the brighter it looks. So this is all fine and dandy, but how does the sun compare to other stars? Because, I mean, according to this, the sun is like the brightest thing in the universe. Well, that's apparent brightness, right? We need absolute brightness. So how can we do that? Well, we have to compare apples to apples, or oranges to oranges, or stars to stars. So we have to set everything to a certain distance away. Now, for some reason, they chose 10 parsecs, right? So 33 light years away. So if you take the sun and you put it 33 light years away, what is its brightness? Right, well, it changes from 26.7, sorry, negative 26.7 to 4.8. That is almost the naked eye limit. Almost where we wouldn't even be able to see the sun if we put it that far away from us. And then we have to take everything else and compare it at 10 parsecs away. So the absolute magnitude is, basically the apparent magnitude at 10 parsecs away.